to the cloud. So I guess I got to share it with you guys. You might be able to. I don't know. That's interesting, Mohammed. I'm not sure. You shouldn't be able to, but apparently, yeah, I wonder why it's letting you do that. I don't know. I don't think it's supposed to let you do that, but I'd have to go and just don't do that. -10 every time. Just kidding. -1,000 every time. Automatic F. We'll have to figure that out. I don't know why that's doing this. It's not supposed to, because over the summer we were trying to do that and it wouldn't work. You guys can't even see what the hell we're talking about. Let me remedy that. All right, so anybody in the waiting room? No. Chat. Okay, so let's get started. So first things first, I want you to know I put a homework up. It's long. Some are easy, some are actually pretty challenging. So this is, you know, I mentioned this before. It's kind of worth pointing out again. You know, this class is in many ways going to be one of the more difficult classes that most of you take. And there's a few reasons for that. The joke always was when I was in school that it's this and OChem are the two hardest classes. I don't know. I think the thing is, in this class, there's a lot of things that you're going to be required to do, and a lot of them, there's very few things that are just simple. There's a lot more mathematical thinking that's happening, and a lot more less just procedure memorizing, if that makes any sense. So, nonetheless, homework 2's up. We're going to talk about some of these problems, but before we do that, let's recap. So last class. We computed the volume of a pyramid. Using integration. And the key idea here is, you know, I would highly encourage that you can reproduce that. It's not easy. And look, we took about, what, 40 minutes to go through that? And it may be the argument was a little over your head, and that's okay, but my advice would be for you to be able to reproduce it, because what's most important is it might even be worth your while to do it for a pyramid that doesn't have a square base. And so why is that, you know, sort of what I would encourage you to do? And that's because the learning experience comes from understanding why it works. Because on homework 2, you can get by just by learning how to do these types of problems. And you can go to the internet and find solutions of similar problems. But that's not really what's important. That's not what you're going to take from this class if you try to take anything from this class. What you want to take from this class, particularly the stuff we're doing now, is why is it that we can solve problems in geometry and in problems in things like physics? Why is integration not just important, but why is it necessary? So that's what I would encourage you to think about. So nonetheless, I guess I can be more specific. So that is why does the formula, I'll write it on the next page. Why does this formula that we wrote down at the end of class Why does it make sense? So, you know, if I were working on this with my own kids or someone in my life that was in, you know, not to, to be honest, I shouldn't say that, because you guys, your sort of performance in this class is important to me. I'd like you guys to appreciate what we're learning in here. I'd like you to care. I know that not every one of you is going to do that, but, you know, in an ideal world, you guys, you're learning it, you know, I want you to appreciate this stuff. I want you to learn it. And so what I'm telling you is just learning how to do examples in the book and just learning how to do homework problems, or at least at minimum copying their solutions off the internet. That's not learning. You know, that's just sort of mimicking something. Not that that's a bad thing. You know, that helps you learn, but the more important thing is the bigger picture. So let's do some typical examples that are similar to your homework, and then we'll do some other stuff too. So where'd my color go? So let's look at a pretty straightforward example. So oftentimes they're worded like this. So the region bounded by y equals let's say quantity x minus 1 squared plus 2, and the x-axis on, let's say, 0 to 1 is rotated about the x-axis to obtain a solid. What is the volume? So let's look at how we might solve this problem. What I would always encourage you do, and any chance you can, is to draw a picture. What's that? You want me to go back? Yeah, that's cool. Yeah. Take your time. Let me know when you're ready. No rush. Yes. Sure. Did I post any what? No, that's a good question. I did not yet. So the question was asked, did we have any quizzes yet? I have not. And funny story, I was working on them last night, and I wrote a quiz for you guys, like a Calc 2, but I put it in the wrong stupid class. So, and then there's no way for me to copy and paste the quiz, so I just had to delete it all. So again, these quizzes will be super easy. They won't be difficult, hopefully. I mean, some of them might be challenging, but most of them are going to be super easy, stuff like that. And no, Emily asked, is Math Labs up? Not yet. I apologize about that. I completely forgot to open it up. It's ready. I just have to click on the button. So I will do that. Someone send me an email and remind me, and then I won't be lying to you, because I told you Tuesday it would be up Tuesday evening. So I apologize about that, Emily. Do not be mad at me for such things. Okay, very good. So let's draw the graph of this thing. And I will remind you, always make a sketch. When possible. Now, you might say, I don't know how to sketch this. Well, this is not a very, very difficult guided graph, but if you don't, that's fine. You can use Desmos, but let me just remind you how, you could do this using some just pretty straightforward ideas you learned in previous classes. So this is a parabola. It's opened up. I know that. It's shifted to the right one. So let me just remind you of what this guy is. This is f of x equals x minus 1 quantity squared plus 2. So it's a parabola shifted right 1 and up 2. You might remember that stuff. You might not. I'm not sure. So if I sort of put some, what am I interested in? I'm interested in what's happening from 0 to 1. So, this thing is, I'm not going to draw it to scale. It's not that important that I do. But what I know is when I plug in 0, I get 3. And when I plug in, say, 1, I get 2. And so this parabola, if I switch colors, is going to look something like this. Now, I'm only interested in what's happening between 0 and 1. So let me shade that region in. I did say 0 and 1, I believe, right? So let me just go back real quick. Yeah, 0 and 1. And so here's what we're going to do. We're going to rotate this creature around the x-axis. That's what we're going to do. And when we do that, we're going to get a solid. And again, this requires some imagination to sort of to do this, but what I would encourage you to do is you try to do that. So I'm really looking at this piece, and then if I think about what it's going to look like, I'm imagining a mirror image of it down here. And it's sort of going to look like a volcano tilted on its side, or a mesa, if you remember these words from like your heydays in middle school and high school, maybe geography, what do they call that? Physical science class. So in order to try to draw 3 dimensions, I'm going to like highlight some of these things. Or maybe this looks like a tree stump turned on its side. You might want to think about that. And so a good way to envision what's happening here is to imagine over here in the red, I put like a little rectangular strip. And I asked myself, what happens to that strip as I rotate it? What does it do? Well, it's going to trace out. So if I take some little rectangular strip, what this strip is going to do is you would imagine, imagine my pen being that rectangular strip. And so what happens is the bottom of that strip is fixed to the x-axis. So when that pen, what it's going to do is it's just going to rotate down and then back up through. And so it's going to create over here, it's going to create what we call sort of this circular disc. And so we have to try to provide some sort of depth to this as well, which is hard, but you get the idea, I think. I hope you do, and I hope maybe those videos we showed last class. But ultimately, me doing an example or two is not enough. You're going to have to really think about these. You're going to have to understand that the better you are at imagining these things, the easier it's going to be for you. Okay, now, I drew a picture, although I didn't really have to draw a picture. But what this picture does do is it confirms to me that I understand each one of these slices. Each one of these cross sections is a disc. It's a circular disc. And as we pointed out 2 classes ago, last Friday now, these circular discs, we know their volume. Their volume is the area of the cross section that we see times its thickness. And that thickness would be what we could call it dx, we can call it dy, depending on, here it would be more of a dx, right? But nonetheless, we don't have to go through all that. We did all that hard work with the pyramid. The pyramid was trying to understand all the scary hard work behind the scenes. But we have this formula now. I skipped this green formula. This tells us what's happening. Because all we need to know is, oh, that's right. The area of a disk, of cross section, the area would be what? It's going to be pi times radius squared. So that's why you see pi f of x squared. Because this distance from here to here is going to be the radius. And this is, of course, x comma f of x. So when my pen rotates around, that becomes the radius of my disk. So this disk of radius f of x. And so that means the area is pi times the radius squared. So that's the way you want to think about this. Actually, I shouldn't say that. Maybe you have a better way of thinking about it. I don't know. That's the way I like to think about it. I shouldn't say that anything is the way, because oftentimes there's better ways, right? There's always someone that has a better idea than you. You might think it's not the case, but it does. There's always someone faster than you, smarter than you, stronger than you. That's life. All right. So I wanted to draw this picture just so I can help reaffirm to myself what I'm doing. But technically, to solve this problem, you wouldn't need to draw the picture, although I think it's worth your time. Okay, so now we got to go, let's calculate. So we calculate. This one's going to be a pain. Volume equals 0 to 1 integral, and then it's pi times the function. So this is going to be scary. It's x minus 1 quantity squared plus 2 dx. And then I have to square this whole thing. Now, I have a couple options here. Do I want to do some algebra? How do I want to handle this? There's a lot of ways I can handle this particular problem. So the way I'm going to do it is I'm going to do some algebra first. I'm going to figure out what that thing inside the square root looks like. So this is also good practice. The first thing you should also note is you can pull pi out. It's a constant. So inside of this, I have x squared minus 2x plus 1, and then this is plus 2, quantity squared. So again, I just multiplied that out. Does anybody have any questions about that piece? So you should verify that for yourself. Okay, now to save time, and you can verify this for yourself too, we will just skip a step. So you should fill in the details. When I square this now, this is x to the 4th minus 4x cubed plus 10x squared minus 12x plus 9. Now, I did not do that in my head, so don't think that I did. So I just didn't want to go through it because A, it's an algebra problem, and B, I want to save time. So you should verify this. Although I guess technically I could have done it in my head. I just wouldn't have done it that quick. So, okay, now this is actually not a very difficult integral, even though there's 5 pieces to it. Oh, I don't want that. I want black. So what is this integral? It becomes 1/5 x to the 5th minus x to the 4th, the 4's cancel, plus 10/3 x cubed minus 6x squared, and then plus 9x. And this is between 0 and 1. And so if I just plug in my 1, I get pi, and then it's 1/5 minus 1 plus 10/3 minus 6 plus 9, which is plus 3. So again, this is not exactly terribly difficult arithmetic. You could probably do this, well, maybe not in your head. But nonetheless, calculators, if you need a calculator, you can use that to assist you. 1/5 and 10/3 is what? Well, you need to put it over 15, so that's what? So 3 and 5, so 53, and then you're going to have a 2 over 15, so it's going to be 83 over 15. So you'd write that as 83 pi over 15. Yikes. Now, this problem was a little longer than a few of them because we had an ugly function we had to square. It was an algebra. The difficulty in this particular problem is more algebra than anything else. If you look at problem 1 on the homework, it's not going to be as tedious. Problem 2 won't be as tedious. Problem 3 won't. 4 won't. Yes. I got 83 pi over 15. Can you not? Yes. Let me rewrite this. Huh? I know. Let me fix that. My apologies. It's kind of, sometimes I forget that you guys don't, it's blurry too. So this becomes 83 pi divided by 15. Is that better? Okay. Sorry about that. Yeah, feel free to complain if things don't, you can't see them. That's what you're paying for, right? I think. No, actually, you're paying for a sheet of paper that says, hire me. Give me a job. Pay this man or woman. Any questions about this? Now, again, this one was a little tedious because of the function I used. It had a square, and then I was squaring it, right? So I was squaring a quadratic, which algebraically becomes a pain. But typically, you don't have to do that. You don't have to do that in problems 1, 2, and you don't have to do that in 3. One problem on this homework that definitely stinks is number 5. That one is an algebraic nightmare. Okay, but you should work it out by yourself without any assistance. Does anybody have a question about it? Comment, question? Good. All right, let's do one more, and then we have to talk about some other strategies. Okay, so here's one that is pretty straightforward. So the region bounded by y equals the cubed root of x so let's say the region bounded by y equals the cubed root of x and y equals x in the first quadrant is rotated about the x-axis. So determine the volume of the solid. So once again, we're going to need to draw a picture. Well, you don't need to, but it helps because this problem is slightly different than the ones we did, or the one we just previously did, because you'll notice this region, instead of being bounded below by the x-axis, it's going to be bounded below by a line. So let's, again, some of you may not be as quick at this, but you should strive to kind of understand this stuff. So if I make my x-axis and my y-axis, so the line y equals x looks like this. Now, it may take some reasoning on your part to know what the cubed root function looks like, but the cubed root function looks like this. It comes up like this, and then it comes down like this. And so the area that we are interested in is this piece in the first quadrant right here. That is the region of interest. And it just so happens that these guys intersect at this point, which is at 1. And you could verify that pretty easily just by plugging and chugging, but that's what it looks like. And so what happens then when we rotate this creature is we are going to get a pretty interesting solid. It's going to sort of look like some sort of flower almost, because it's going to come down, the top part comes down like this, and then the bottom part's going to come up like this. But then we notice that there's going to be sort of a hole in here because we're not rotating this little triangle area where it's not shaded. There's nothing being created there. So that red curve is going to generate sort of this sort of hollowness to our shape. So there's sort of like a little bit of hollowness there, if you will. So what I'd like you to think about, and please ask a question if you're at all sort of curious of what's happening, or if you're confused, I guess is a better way of saying it. So if I take some sort of like rectangle here that y'all draw in purple, what this does is this generates sort of this purple disc when it rotates about. But in that disc has an interesting feature that it has a hole in it. So this disk has a hole. And so there's a name for that in the English language. It's called a washer. So what I'd like to do over here is let's sort of draw that washer in a bit more detail. Sort of is going to look like this. So we often call that a washer because there's a hole. And the beauty of that is it's okay because it's still very much a simple geometric object. It's a disk with a hole drilled out of the middle. So all we have to do to understand its cross-sectional area is think about the area of a circle and then subtract out the circle that we drill out, right? So what this leads to is it leads to a very simple formula. Because you can think of this in a few different ways. You can think of the volume of this shape as being the volume of one solid with the cone drilled out of the middle. Or you can think of us just tracing a solid. Either way, well, without much thought, there's a very sort of natural extension to what we did before. So what we think is the following, sort of, you know, and I'm going to try to be pretty thorough here. The volume should be the integral from 0 to 1 of pi, and then we'll put, let's be even slower. Let's not even jump to that piece yet. Let's say the cross-sectional area right now. So if I go back to the previous page, what's the cross-sectional area? Well, the area is pi times the radius, but what's the outer radius? The outer radius is cubed root of x squared, and then you have to subtract out the inner radius, which is pi times x squared. So again, imagine, don't overthink this. Imagine you're in an elementary geometry class in middle school, and you have a circle, and then you want to take a circle out of the middle. What would be the resulting area? You subtract the larger one, excuse me, you subtract the smaller from the larger. That's what we're doing right here. So that's exactly what's happening here. This just becomes, integral 0,1 of pi times the outer radius squared minus pi times the inner radius squared. So let's annotate that. So this would be the inner radius and then of course this guy right here would be the outer radius. So that's how I would encourage you to sort of think about it. And now, once we get to this point, it's kind of pretty straightforward. This is going to be an easier integral than the previous example. You can factor out the pi, and you're left with x to the 2/3 minus x squared. And then this becomes x to the 2/3 plus 1 is 5/3. So this becomes 3/5 x to the 5/3 minus 1/3 x cubed from 0 to 1, which is pi times 3/5 minus 1/3, which is pi times what? So what, 9 minus 5, which would be what, 4/15? 4 pi over 15. We believe. Let's double check our work. I think it's correct. Hopefully you can verify for yourself. So here we go. That's a sort of it's a similar problem. Now, what the book does is it just tells you to memorize these formulas, and that's fine, but I just think that's a bad way of learning. The better way of learning is understanding how all this stuff, these formulas come about. They come about from what we really suffered through on Tuesday, which was this pyramid type problem. Now, of course, most of you, because it's human and you're amateurs, is you're going to say, I don't understand how any of this comes from that, right? And that's okay. The understanding part is the hardest part. Memorizing procedures is not hard. Understanding is difficult. Now, the downside to memorizing is that you usually don't remember anything 3 months from now. The plus side of trying to understand things is that typically later on in life, you can refer to them and get use out of them. Does anybody have a question? Someone's chatting. So the question is, why do we multiply with pi? Because if you go back to the problem, the area of a circular, so you imagine that, we'll start from the basics. The idea is, if you look at this graph, I have this little purple rectangle. And I would imagine this pen as being that rectangle. And what happens is it rotates around the x-axis, is it comes down and back up and around. And what it does is it traces out this purple disc, sort of, that I see here on the right-hand side, and that I brought out over here on the left-hand side. Now, it's really not a disc because the disc has a hole in it. Why does it have a hole? It has a hole because this triangle under the red line is not adding anything to the problem. So the thing is the volume of this disc, is going to be the area of its cross section. Well, it's a circle. And so what is the area of a circle? It's pi times radius squared. And so that's where the pi comes from. The pi comes from the fact that the cross sections have area of pi r squared. So hopefully that makes sense. If it doesn't, let me know. Does anybody else have a question about this problem? So a cool consequence of this, which baffled lots of people on this planet for a long time, is how many solids that are in our daily lives that their volume depends on pi. It's quite fascinating. So in fact, in many ways, nearly any solid that has a curved boundaries, its volume is a multiple of pi. It's pretty interesting if you think of it that way. All right. So let's motivate another sort of situation that can arise. Okay, so to motivate another method for determining volume, let's consider the following problem. So let's take the region bounded by, let's say, y equals 1 minus x in the first quadrant. So instead of rotating around the x-axis, let's rotate about the y. And what we're going to find is if we try to do what we did in the previous problems, it's not going to work, algebraically at least. So we want to come with a different sort of strategy. So let's get our y-axis and x-axis drawn up. Stuff is so much fun. So we'll draw this line. So this is the line y equals 1 minus x. When you plug in 0, you get 1. When you plug in 1, you get 0. So the only region that makes any sense here would be, if we're in the first quadrant, would be this. So let's remind ourselves that this is the point 1, 0. This is the point 0, 1. Okay, so now what we're going to do is we're going to rotate about the y-axis. And so when we do that, what we end up getting is we're going to get sort of like a cone. In fact, it's not sort of like a cone, it's going to be a cone. Now, the challenge here is what worked for us in the previous couple problems is we were taking these slices of our solid and we had a simple formula for its cross-sectional area. So the thing that we might say here that is different than the previous problems is how should we slice? In particular, let me rephrase that question. How should we slice in order to obtain a simple formula for cross-section? In particular, this thing we've been calling A of x. Can you guys read that? You good? So notice what we did in the past isn't going to work here, because if I take these vertical slices, I'm going to see there's no pattern. So one idea would be to take horizontal slices, and that will work. So again, let me reiterate that. Imagine you have a cone sitting on the ground just like this, and you want to chop it up and look for a pattern. If I slice it vertically, there's not an obvious pattern. Now, there is one if I slice it horizontally. And that would work. We could do that. But for illustrating another method, let's try to think of another way to examine this shape. So let's say the following. So one possibility is to take horizontal slices. You know, another way of saying that is you could just take that cone and turn it on its side, and then it becomes the previous problem. So if I draw that creature again, what do I mean by a horizontal slice? Well, that would be something like this. And the reason we say that this is nice is because these slices are circular. Now, the one issue you run into here is now it might not be obvious what the algebraic formula is, though. So the issue with this So let me be very clear. This works. But it requires algebra to determine a of x. And in fact, we would actually have to write as a function of y. And so that volume would be pi times some integral from a to b of a sub y dy. Or excuse me, I do not need pi there. It's in the, it's actually in the a. Does anybody have a comment on this? And I'm not saying it's particularly difficult or hard to do. I'm just saying it might be a little more work in most cases. So again, you could do it this way. And maybe for fun you try it. But in essence of time, and we don't have much of it, let's show you another possibility. So alternatively, imagine the solid being generated in a different fashion. So that's what we're going to concentrate on now. So if I go back to this page, I instead of taking horizontal slices, I want to use sort of an idea of a vertical slice, but I want to do it in a different manner. Okay, so I'm going to, again, this is one of these things where I've said numerous times, what we often want to do is if we have a problem and we're not quite sure how to solve it, one of the best things we can do is step back and look at it from a different perspective. And that is a strategy that works in every aspect of life. Okay, you know, it's like you're working a job, you feel like you're being worked and not appreciated for your job, and you say, I need to go get a raise. Well, maybe the correct answer isn't to get a raise, it's to step back and go get another job. Or, you know, you're sitting there and you're saying, I hate this, I can't figure this out. And then you go to your boss and say, boss, we got a problem. Your boss says, well, I don't want you to think of it that way. You come to me with solutions, not problems, right? Got to look at things from a different perspective. So let's think about how we might do that here. So it would be in our best interest to sort of draw the situation over again, and that's what we're going to do. So if I draw my XY axis, and then I draw my line looks like this, and then I shade in like I did before. So the thing is, if I wanted to get horizontal slices, the way I would imagine this thing being generated to get my horizontal slices is I would imagine it being generated by taking a horizontal slice or a horizontal rectangle here. So if I wanted if I wanted those horizontal slices, I need to imagine this piece moving around the y-axis. That's how I would get my horizontal slices. Remember, we're rotating about the y-axis. But instead, what I'd want to do is I want to come at it from a different angle. So what I'd like you to do is go back to using a vertical rectangle. Now, if I rotate around the y-axis, what is this purple rectangle going to do? So if I imagine my y-axis is right here, it is going to come out of the board. Well, I guess I'm trying to figure out how you're seeing this. Okay, yeah. So my right hand is the y-axis. So here's the purple rectangle. What's going to happen if I rotate it? It's going to come out of the board, out and around, back in, and then it's going to come behind and around, right? So when I do that, when I rotate just that purple strip, the purple strip is going to generate sort of, whoa, that's very big. So let's maybe try to draw it a little more to the same size. Here's my purple strip. So it's going to come out of the board, around in front of the y-axis, then it's going to go back into the board, and then it's going to go back through and come back around. Does this make sense? So a good way to think about this, if I do say so myself, is imagine that you have your purple rectangle. You can imagine when it comes out and around and back in, what it's forming is sort of like a very thin cylinder, like this. This is sort of what it's going to. This is the image I'd like you to have. That's sort of, it traces this out as it moves around. So we give a name to this. Another way of thinking about this is like a wristband is a good visual for this thing. This wristband. Does that make sense? And so we call this, so let's be very clear. So when the purple rectangle of, say, width, let's just call it delta x. It's some small little thing, right? Remember, we imagine we're using these little thin rectangles. So when the purple rectangle of width this goes around, so it generates what we call cylindrical shells. So if I cut it, this is a great analogy. Thank God for the Roni. We would never have this without the Roni. So here I have my shell, my cylindrical shell right here. And I can imagine that shape being built by a bunch of these. And you may have seen this before. I don't know if you've ever, like, another visual you might have seen, if you've ever, like, maybe not because you guys are all younger, but like I have a home, and when you get married and stuff, people buy you things you'll never use. Like, people buy us all this stuff for baking, and you have like cookie cutters. And they're all like they all fit inside of each other, and they kind of stack up. Or maybe if you've ever seen like measuring cups stacked up, you can imagine that kind of visual. And the beautiful thing is, if I take scissors and take my wristband and I cut it and lay it down, then this cylindrical shell has very simple geometry. So we cut it and lay it down. And so when I do that, it becomes a rectangle that has a very, very tiny bit of thickness to it. So what is the volume here? The volume of this piece is, well, we can imagine what it is if we just carefully trace our steps. So for example, the distance, if this right here is x, then what is the distance? And of course, we're going to say that this thing has a thickness of dx. So we'll say this distance right here is delta x. And then what is the length of this thing? The length of this thing is the distance it's generated. But when we notice that this thing is what? When we put it together, it's a circle. So this is going to be the circumference of a circle, which is 2 pi times x. That's the radius. And then the height of this thing is just f of x. Why do I say the height's f of x? Because you guys know this is the point, x comma f of x. Of course, we know in this case that f of x is 1 minus x. So the volume here is the air, or the volume of this thing, which becomes 2 pi x times f of x dx, which of course is 2 pi x in this problem times 1 minus x dx. So this shows us two things, and we're going to write them on the next page, but I don't want to leave this until you guys have a question, or unless I've answered every question or comments. Let's see, I didn't check the chat. Anybody chatting it up? Is there a way that, like, on here you can ask anonymous things? Like, some of you might be afraid to ask questions. Let's see if we can do that with a poll. Oh my God, let's see. Add a poll. What happened here? I know, I didn't say you necessarily, Emily. I'm saying some people might be. Some people don't like to be. Yeah, I know, but I think they can only ask privately to me. That's true, you can. Okay, yeah, that is true. I forgot about that. Of course, then again, I expect everybody to be like me, loud as hell and obnoxious, and maybe not everybody is. Would you say I'm obnoxious? Amy tells me I'm obnoxious all the time. Did I say that right? Obnoxious. Oh boy, I failed the SATs. Obnoxious. Yeah, so we're getting to that right now, Emily. That's the key point to make. So we through a specific example, through just this one example, not only did we solve the example like we did with the pyramid, but we also see the general formula, right? So let's make sure we understand that. So there's two consequences of what we just figured out. And I'm not saying they're going to be as obvious to you as they are to me. So we discovered two things. The first thing is the volume of our cone that we started with. It looks like this. We found that this is the integral from 0 to 1 of 2 pi x times 1 minus x dx. We found that. And secondly, which is even more important, if we think about what we did on the previous page, we found a more important thing, and that is the general formula. That is, in general, the volume in the correct context would be integral a to b of 2 pi x times f of x dx. And so there's a name for this formula that you'll see in most books, and maybe you can Google it if you want to have more resources. This is often called the shell method. And the reason it's called the shell method, it's because of the way that we generated we thought about this solid being generated using these cylindrical shells, these wristbands. So I think it's at this time it's a good idea to go look at some pictures on the internet real quick, just to get your imaginations sort of running wild as I check the time. Does anybody have a question about this, by the way? By the way, I'll skip the steps here, but you can easily integrate. I mean, this is not a hard integral. And so you should verify this for yourself. I mean, you know, this is 2 pi x and you could pull the 2 pi out, really. So maybe we'll just do it real quick because it's good practice. So this is, oh, let's not use. So what is this? This is 2 pi. We'll pull the 2 pi out, and then what are you integrating? You have x minus x squared. So when you integrate that, that becomes 1/2, excuse me, yeah, 1/2 x squared minus 1/3 x cubed from 0 to 1. And when you solve this, right, but okay, so the point, so Zollfiger is saying we found the area of the cylindrical shell. That's correct. But the idea is, and this is the whole point of what we did last class with the pyramid, is that all you need to know is the volume of one piece, because we know that if we add them all up, we get an integral. So that's why I only needed to know the pattern for one piece, and I can write it right here. Once I know the pattern for one piece, then I could say I'll approximate it by adding up 40 of the pieces, or 100 of the pieces, or 1,000. But what I learn is if I send the number of pieces n to infinity, I get the exact volume, which is given by the integral. So what we end up getting when we plug this in is we get 1/2 minus 1/3, which becomes 3 minus 2 over 6. So that's 1/6. So this becomes, if we do it correctly, pi over 3. So we'll have to double check that in a second. And so what we can do is we'll go to the internet and verify that this is correct. So if we go to the internet, let's switch up real quick. We'll do that later. So let's look at the volume of pyramid. Well, what do we know? What was our base? Well, see, not pyramid. Cone. So what was our radius? Our radius was 1 and our height was 1. And so we get volume equals 1.05, but that's exactly pi over 3. See? Pi over 3, 1.04. And that's what we got. By the way, while we're on the internet, oh, okay, I'm sorry, you can't see. That's a shame. Give me 1 second. What a terrible thing I did to you guys. You guys seeing it now? So our pyramid, I keep saying pyramid, excuse me. Our cone had radius of its base was radius 1, so, and its height was 1. And so when you plug that into the formula, you should get pi over 3, which is what you get. Can you guys see this now in chat land? Yes, no? I can't tell. All right, cool. And while we're on here, it's worth pointing out, we can just Google cylindrical shells, calculus. By the way, you'll see there's lots of internet resources on this. You don't have to spell it correctly, but if we just go to some images, let's see if we can find some good ones. This one looks to be a little, it's not as good as we had hoped. Here, this one looks to, no, okay, yeah, here's a, I don't like any of these. I got a better idea. Here's a good one. See, this kind of gives an idea of what the idea. You can imagine your solid is being built by these shells. Now, these shells that you see right now are thick. So the point is, if you use 10,000 of them, they're going to be extremely thin, like my wristband is. And they're going to better approximate the actual surface you see. And then if you use 10,000 or 1,000,000, it's even a better approximation. And as we let the number of these shells go to infinity, you actually, what you end up getting is the actual solid itself. Okay, does anybody have any questions about this? So here's my advice. Notice I said we have a few methods now for computing volume. So let me give you my advice on this, which is really can't steer you wrong when you're in Calculus 2. This is not a rule. There are exceptions to this, but it is a solid piece of advice. So advice. When the region is rotated about the x-axis, try the disk washer method first. And then when the region is rotated about the y, try the shell method first. That's a good rule of thumb in Calculus 1, Calculus. It's really a good rule of thumb everywhere. It's not always the case, but it's a good way of thinking about it. Now, if you think about these different methods, you'll start to understand why, because what happens is the geometry is usually much easier to work out using disk and washers when you rotate about x, and then alternatively, the geometry is usually more easy to work out using shells when you rotate about y. Not all the time, but often. Do we understand what I mean by this? Hopefully. This is crazy, huh? Crazy, 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 crazy. So that's a good rule of thumb, and I'm not going to steer you wrong either way in this class. If it's a test problem and it's rotated around x, the easiest way. I'm not saying it's easy. I'm saying the easiest way. The easiest method would be disk method. Remember, disk and washer is the same thing. Washer just means that there's two curves that create the region. Disk means there's just one, because the washer means there's a hole. Does anybody have any questions about this? Good? All right, well, listen, I really hope you work on those problems and you ask questions tomorrow for us, all right? Don't forget, Group B is supposed to come tomorrow. So if you guys can try to adhere to that, I'd appreciate it. If you have any questions about my math lab or about homework, please let me know. I highly encourage that you do some office hours with me if you need help. There's no bad questions. There's only good questions. By the way, you see that girl on the internet everyone's making fun of for asking why math exists? Did any of you see this yet? Everyone was mad at her. Oh, it's awesome. You got to look it up. She's asking good questions I wish you guys would ask. Like, why did we do this? Why? Who did this? How did? It's great stuff. You should think about it. And the internet killed her because they said she was stupid. And you got to look it up. She asked really good questions. So anyhow, please reach out if you need help with anything. Hopefully. Oh, also I wanted to say, if you're interested in coming to both all the lectures, and if there's room, I'll allow you to. So just send me an email and all that stuff. But you can't just show up unless you ask, because the social distancing guidelines say that's no. Does anybody know who used to do this in basketball? Oh my God, you have to Google it. All right, take care, guys. Have a good weekend. If I don't see you, hopefully you'll be on Zoom and everything. All right, thank you, guys. Take care. There it is. Ha!